Our team name is Exploring Genetic Design Spaces, and the team members are Evan Bowman, Melissa Garcia, and Erica Schwartz.
Genetic design spaces. A genetic design space is a graph that represents many genetic designs by encoding rules for composing sets of DNA components. Similarly to a graph, a design space includes a set of nodes and a set of edges. Each edge is labeled with a set of DNA components to choose from. Each path, from a start node to a stop node, represents a linear composition of one DNA component from each edge into a design.
For our project, we were tasked with upgrading a pre-existing tool called Knox. Knox's primary task is providing a variety of operations for editing and combining design spaces, including join, or, and, merge, repeat, and delete. We focused on 4 main tasks. 1. Simplifying the user interface and creating a more aesthetically pleasing and easy-to-use environment. 2. Expanding the enumeration method to allow for more user specification. 3. Refactoring the genetic design space sampling method so that it now uses edge probabilities. And 4. Allowing a graph to be clustered into highly connected components.
We added many different functionalities for the user interface. First, we added a landing page to Knox, which introduces the app and gives a brief overview of its functionality. Users can click the Explore button at the bottom of the page or use the page's navigation tabs to start using the web application. On the Explore page, a search box provides quick access to all of the user's saved design spaces. We also added search suggestions to make finding design spaces easier. We've rebuilt the graph visualizer. It now has a cleaner design, uses the vector versions of SPL visual icons, and supports a few new features, pan and zoom. Buttons at the bottom of the page provide access to features for creating and deleting graphs. The Merge button allows users to combine the current graph with another one, using one of the methods supported by Knox. The Delete button removes existing graphs from the repository. Previously, the enumeration method for Knox was pretty limited. It only allowed for a breadth-first search and was completely inaccessible from the front end. Now, the enumeration method has been extended to allow for 2 user specifications. Users are allowed to choose between a depth-first search and a breadth-first search, and are also able to specify the number of designs they wish to see. These results are then displayed to the user on the front end. We created our own algorithm for the depth-first search that works by creating permutations of all paths in a tail recursion format. The complexity of this is difficult to analyze due to the presence of multiple component IDs for each edge. If we assume each edge has only one component ID, then the runtime is limited by n factorial. Another way to explore the design space is to enumerate designs using user-defined probabilities for each edge, thereby sampling the space. We created a method that uses a start node as a starting point, and then picks edges using a random weight sampling algorithm. First, the probabilities of the edges are summed to get the total weight of the edges. Then, a random number between 0 and the total weight of the edges is chosen. Finally, the edges of the particular node are iterated over, summing up the probabilities. This final loop completes once the probabilities are equal to or greater than the random value chosen in the previous step. In this way, edges are chosen from a start node to a stop node. If a graph is very large and dense, it's difficult to visualize the design space, and even more difficult to draw any meaningful conclusions about design patterns just from the design space graph. By clustering highly connected nodes, it organizes the design space in a purposeful way. In addition, this algorithm can be useful in allowing the user to further abstract the design space. These highly connected components of the design space could be grouped together into separate functional units, such as transcriptional units or genes. In Knox, we implemented the Markov clustering algorithm for this purpose, which uses Markov chains to simulate random walks on the graph. The idea behind this is that if there are natural clusters inherent in the design space, then a random walk will infrequently go from one natural cluster to the other. The algorithm starts with an adjacency matrix representation of the graph, and then iteratively computes the probability of random walks through the graph. After a number of iterations, the matrix approaches a steady state value, and then we can determine which nodes belong to which clusters based on whether the probability of the random walk from node A to node B is high or not. That's all for now. We hope our efforts to enhance Knox will be useful in the future. Thanks for watching.